Welcome, sir. Nobody is there today.
What is here?
Nobody is there.
So we don't have to teach today.
No. It appears it's getting too much further now.
Sorry.
They are getting tired, I think so. Too many classes.
Too many classes.
Maybe.
We'll cancel it or we'll wait.
We will wait and sending them message.
Sorry, I mean your voice is not clear.
Sumbul, how are things going? Really, Sumbul? How are things going?
Hi, Dr. Ruhi. So which university are you from?
Nagpur University, Maharashtra, India.
Nagpur. Okay, thank you. So you are working in electrical power system or in other area?
Yes, sir, electrical power system.
Okay.
Sir, I believe we can start.
We have got good number now. 20 is a good number to start.
And sir, tomorrow we'll have a valid 3 p.m. So
Mm-hmm. Yeah, I saw your invitation. Anything you would like to mention about that, or? So, Altaf, can you confirm me whether you can see my screen?
Yes, sir, we can.
And also you can hear me clearly, right?
Yes, sir, it's clear.
Okay, thank you. So, again, welcome and good afternoon, everyone. So today I'm going to talk about microgrids. As you know, this is, it's not new, but it's comparatively new technology. Although, I mean, there are already many residential commercial microgrid are operating in different countries. But still, I mean, there are still some, unresolved challenges. So if you are interested, this is also a, I mean, good topics. I mean, if you would like to work either in your master's or PhD, or even if you are academics, there are, many challenges that you can work on in this area. So before starting, can I ask you whether is anyone here, I mean, working in microgrid? It could be either DC-AC, microgrid design, control, or even could be feasibility analysis, or anyone is interested to work in microgrids.
Sir, my work is in DC microgrid voltage stability.
Okay, I think, yeah, that's a good topics because AC microgrid, I mean, because we have got AC system, so AC is quite established. So DC definitely that's DC microgrid stability, DC microgrid protection. Yeah, that's definitely that's a good topics. Thank you. Anyone else from here is working in microgrids? Anyway, even if you don't have any idea, I think this is not a very difficult concept to understand. So if you have got any question, comments, feel free to interrupt me anytime. So as usual, I always start from the very basic. So I'll discuss about its advantages and challenges compared to the normal power grid. Then I also talk about how can you design it. I'll also talk about its energy management and control. Because when you have microgrid, mainly in the isolated or off-grid mode, the control is a complex issue. And then I'll show you some research outcome from my group on microgrid. I have already shared the slide, but if anyone even would like to go very deeper about microgrid, these are the two good books on microgrid. So whenever you have time, I mean, you can also have a look these two books as well. So these are the contents for my today's talk. I'll just start with issue that's traditional grid are facing now, how microgrid can address some of the challenges that the traditional grid are facing in current year with large scale renewable. And then I'll also briefly talk about distributed generation, smart grid. I mean, microgrid is also a part of the overall smart grid. So this is actually just showing like that Australian power grid. So the Australian power grid is one of the longest grid in the world. So it has got more than 5,000 kilometer long transmission line. And here actually all the state, including Queensland, New South Wales, Victoria, and then the Tasmania. Tasmania is an island, but it is connected with a underground high voltage DC. And then South Australia. So only one state is not interconnected, that is Western Australia, because that's very, very far from other state. So this is all are interconnected. and it has got different level of voltage level. I think the maximum in Australia is 500 kV, but in many countries like China, they have got even like more than 1000 kV transmission line. And this is like the capacity of, here the electricity market in Australia we have is called National Electricity Market. That represent all the state except Western Australia I mentioned. And this is the way, the current demands looks like. But again, this is up to 2017-18. So as this information I already mentioned, like that PV capacity is going up exponentially, and not only PV but it has got wind as well. So as you know that when we have got large scale PV and wind, it is actually creating number of issues for the grid, and microgrid could be a potential technology that can actually solve some of the issue that is being introduced by photovoltaic system and wind turbine. So as I mentioned, this is one of the longest transmission line in the world, like 5,000 kilometer long. And the other things, I already discussed about its renewable energy penetration level and so on. But one thing you might know that the world biggest lithium ion battery, that is actually in South Australia, where we have got a single 100 megawatt capacity, and in terms of megawatt hour is 129 megawatt hour, and that is being installed by Tesla as like they are like a demonstration system. That's just quick about Australian power grid. Now even if we talk like in Australian power grid or the conventional system, it looks like that. So you have got centralized power plant, and then you have got load center, and this centralized power is transmitted via long transmission and distribution line to the load center. So in most of the cases, the power station are far away from the load center, and there are many reasons for that, because again, we don't want that coal or gas power station in the area where people live, and also it depends the area that's all the input resources are available, just to reduce its transportation cost and so on. Now, if you have a system like this, what are the what problems? What are the issue? When you have got this type of system, there are actually a number of issues the current grid has. That's why now we are going for alternative forms of grid. One of the problem is that it has got very high transmission and distribution losses. As you know that the losses is I square R, and R is nothing but the resistance of this line. So if you have got a longer lines, you will have higher resistance, and that's how you will have got higher losses in the system. So in many cases, like some country, even in India, it was like more than 10-15% losses in the transmission distribution system. And that's if you convert into dollar value, that would be like say yearly millions of dollars annually. So that's a big loss for the power industry. But it's not for power industry actually. That cost actually come to the consumer at the end, because power industry is not paying from their own pocket. They are passing that losses to the consumer. That's one issue. Other issue also, like its reliability and resiliency are not high. It also not that flexible, and it is definitely not environment friendly either. So that's why I mean all countries now they are looking for alternative option. So this is I already mentioned like that higher losses, lack of flexibility. It's a very long line and that's why it's a complicated stability problem. Energy price is high and most of the system have installed and constructed many years back. So that's why most of the infrastructure are old. So aging is also a issue for the current grid. And other biggest problem is that the grid user, mainly the consumer, they are like a passive participant. They are just using whether they like it or not. Yeah, so they don't know exactly what is happening inside the power grid. So as I mentioned, like in many countries, this is like on an average 8 to 10%, but many countries it has got more than that of their total energy is lost. So if you have like megawatt, gigawatt, I mean in that range, 8 to 10%, that's like a big number. And just here for in USA, just one example that if their grid was 5% more efficient, the energy that could save, I mean that would be equal to permanently eliminating the fuel and greenhouse gas emission from 53 millions of cars in USA. And another example that if they replace their old like fluorescent bulb with that another I mean energy saving light that you can get now with the same, that's more like 3 millions home can be lighted with that same amount of energy, and it could save more than 600 million annually. So just replacing those light. So that's why I've said like if you convert that one, that's like a very big number. And as I say, like I mean in even like in 2001 in India the losses was 30%, but in 2013 I mean it has gone down significantly, and I believe now even it would be lower, but still it's higher than other developed countries. You can see this is like more like the average. As I say, like it's close to 10, but it's slightly less than 10%. So on an average, like 8 to 9%, that's the world average. So not only that, as I said, like there are number of blackout that happens in many countries, including India, Australia as well. So in India, I think one of them was in 2012, where like northern and eastern part of India experienced blackout. And it's not that in India, but in some other country in Bangladesh, there is like a rolling blackout as well, because in many cases they are total generation less than the demand. So that's why they just roll out blackout in different places. Recently there was in USA, in Australia also, like in 2000, I think 13 or 17, there was like a big blackout as well. So this is also, I mean, one of the challenges for the current grid. And I already mentioned about that environment and climate change issue, because power sector, that's almost contribute 1/3 of the total, greenhouse gases. So if you think about like the microgrid smart grid, that can address many of the problems that I mentioned here. So if you think in the current power grid, these are the some of the changes that is happening due to the energy transition. So as you know that in the power system we have got mainly three major parts. One is generation, another is transmission, and third one is the distribution. And even in the distribution side, after meter, we have got the end user. So in all of the parts of the power system, there are a number of changes happening. So if you think about the generation, as I mentioned, like in the current power grid, most of the generation is coming from centralized, large scale fossil fuel generation. But in current year, this fossil fuel generation is being replaced by a small capacity renewable energy sources. So there are massive changes happening in the generation side. The transmission side, the transmission side is comparatively intelligent in most country, but still in the transmission side also there are many changes happening. For example, you'll find many monitoring system, for example, phasor measurement unit, power electronic based controller like FACS devices. So as I already mentioned, like STATCOM, SBC, and also there are other types of FACS power electronics controller in the system as well. So power electronics is like a very, very important part of like the future power system. And then in many countries, like mainly in Europe, they are going for a high voltage DC transmission instead of high voltage AC, because high voltage DC have got number of advantages when you have got very long transmission line. So if you have got a comparatively a smaller transmission line, then AC would be more economic than DC. But when you have got very long transmission line like Europe, they are like all Europe are would like to be interconnected. So in those cases, high voltage DC is better, because here losses is lower, and it has also got the control capability, because here also we are using like initially AC to DC, and then we are transmitting as a DC, and then we are converting DC to AC, because most of our load is also AC. So that's why it has got the control capability, both active reactive power. But actually the biggest changes are happening in the distribution side. So in the distribution side, you are getting many distributed generation. You are also having like microgrid. This is the topics for today's discussion. You are having a smart meter, which is also like very popular. New technology that's coming in the power system, because here using a smart meter you can monitor and not only monitor, but in some cases you can also control your energy consumption as well. And also you have got real-time information, like how much energy you are using, which appliances using how much energy, what are the individual electricity bill you are paying for different appliances. So that's actually giving you some good information about your energy consumption pattern. And if you would like to save some money, through that observation also you can decide on that. And also it's giving like when energy price is high, when energy price is low. And then new loads, that's we already talked about that. Plug-in high electric vehicle or pure electric vehicle, that is also being integrated in the distribution system. So if you would like to work on like on the power system side, then I think most popular topics that we'll be getting in the distribution side, because distribution system is not that intelligent, and in most of the cases we don't have enough monitoring device in the distribution system. We don't have good model to analyze that distribution system. So here there are many challenges needs to be addressed. So if anyone would like to do master's PhD in this system side, then I think you can think of working in the distribution side. So even after the meter also, many things are happening. One of them is energy efficient home. Probably in fact you think that most of the new homes that are building in Australia now, they are actually integrating many of these new IoT devices, and also like the better design, how we can also have maintain the temperature using shading, and other things without using AC. So that's energy efficient home. That is also a good topics now. And then you have got building energy management, zero energy home, and then energy pricing and so on. That's we talked yesterday about transactive energy, and also we are having new policy and so on. Other things also happening that people are now more aware of environment impact of generation. If you think about 5-6 years back, so now everybody is understand what is sustainability, what sort of impact it is the current power system having on our environment. So again, these are the some red bullet points that if you are interested, you can think about working on those topics. Now I'm moving to microgrid, but so far, is there any question or comments? Okay, if not, let's talk about microgrid. So there are a number of definitions are available in the literature. But again, the simple way to understand that this is nothing but a smaller version of the main power grid. So the main power grid, I already mentioned that it has got generation, transmission, and then load. Microgrid also have the same thing. Microgrid has got generation, then it has got like a small, it might have a small line, because load or generation are almost located in the same area. Okay, so that's why it's like a comparatively small scale power supply network that is designed to provide power for a small community. It enables local power generation. That's, as I say, loads or generation are located at the same site. It has got mix of small, power generating sources that make the system more, flexible and efficient. So it has got the capability either to connect it with the main grid or it can be isolated. So if it is connected with the main grid, you have got the option to sell excess power back to the main grid, or in some cases you have got the shortage. You can buy from the main grid as well. But when I'm saying like the microgrid, many people ask about actually what's the size. The size actually here is from because microgrid could be like any small scale, could be one house, it could be a small community, right? Or even sometime it could be like your university campus. So there are, it could be a different size of the micro you might have it. Now this is just like one typical example in microgrid in Australia. So here you can see that it has got a photovoltaic system. It has got battery energy storage connected with the PV. And then also you have got here, this is the substation which is connected with the main grid. So here you have got a switch, either it can be connected or disconnected from the main grid. And then you have got like different loads, which is connected with the microgrid. So as I say, it has got both sources and load, and a small line would be connected as well. So it seems like a mini version of the main grid. This is another example. This is a research microgrid that we have got in New South Wales. So we have got a research organization. It's called CSRO, and actually we have got number of project with them. So they have got their a own experimental microgrid setup, and here also you can see they have got wind turbine, lithium-ion battery, solar. They also have gas turbine. They're also having virtual power plant with them connected, and then they have got vertical axis wind turbine, gas turbine, solar plant. Here also have got some test load bank as well. So this is more like if you would like to develop something and if you want to test, this is like a test microgrid. We could use here at New South Wales. Now this is giving the microgrid prospect for the a whole world. So in terms of percentage, worldwide, Australia is contributing a lot, like a 12% of the whole world. So 44% in Central and South America, but Asia also have got some microgrid in Asia as well. But as I say, this is getting popular in recent years. So in coming years, I know you will also find more microgrid in India as well as in other countries. Again, this is some of the microgrid project in Australia. So here you can see this is some for a remote community, some for research purpose, some for tourism, but most of them for the remote community. So this is one of the world accepted definition of microgrid. So this is a group of interconnected loads and distributed energy resources which has got clearly defined electrical boundary that acts as a single controllable entity with respect to the grid. So what it mean here, that you will be having interconnected loads and distributed energy resources, that's I mentioned, but it's having a clearly defined electrical boundary. And the whole microgrid is act like a single controllable unity. If you think about with the main grid, and this is some of the things it's come from that definition. So as I say, you can either operate a grid connected or isolated mode. It has got number of advantages in terms of efficiency. It's much higher than the conventional power grid. And also here, in most of the cases, the heat which generated, you can also utilize that one heat, but in the normal power grid, there are massive amount of heat is wasted in the conventional grid. And power sources here, as I say, is most of the cases like a micro sources, very small and connected to the close to the load center. That's why it's more economical. And also when there is any problem in the main grid, you can disconnect the microgrid and you can supply to the local community, mainly you can supply the critical load. That's why it will be more reliable and resilient. In peak periods also, it can helps the main grid failure by reducing the load on the main grid because it can supply their own loads from the microgrid, and it has got significant environmental benefit because most of the sources, either having very low or even like, zero emission. Yeah, that's I already mentioned, but it has got some challenges as well. Mainly during the isolated period, that voltage, frequency, and the power quality. These are the main three challenges that you have when you are mainly operating in the isolated mode. And also isolated mode, I mean, you need energy storage device to make it like stable, mainly during the off-grid operation. And also, I mean, when it is operating in isolating mode, and again you are coming back to connect with the main grid, that resynchronization with the main grid is also difficult. So you need like better control to do that. And I was saying like that it should have like a clear boundary. And here also you can say like different microgrid scale. As I say, like few homes, even like a single home, as I mentioned, like it could be a microgrid when you have got generator and and a photovoltaic and photovoltaic system as generator, as also like a battery with them. But with only photovoltaic system, we can't say this is like a microgrid. It could be a group of homes, like a partial feeder microgrid, and you can see that this is on have got a clear defined boundary. It could be like a full feeder microgrid, like this is a feeder, so you have got like a full feeder, or even it could be like a one full substation. That could be a single microgrid as well. So that's why it's in terms of kilowatt or megawatt, the capacity could be different. Now, if you think about microgrid components, these are the main components of a microgrid, the distributed generation, which is, as I say, like it could be wind, solar, small, sometimes diesel. Sometimes it could be also like a small hydro. It has got different types of load, like the normal grid it has. It has also like storage, as I mentioned, and the control. That's like in a very important part of the microgrid. And then the point that is connected with the main grid, we call it point of common coupling. Probably I saw a question in the chat box, because I cannot read that chat box. I mean, if you don't mind, can you please unmute yourself and ask the question?
How are the boundaries decided of a microgrid?
Well, I mean, it depends on your requirement and design. So if you think about like, you would like to have a microgrid for a community, then I mean, you'll see like, like let's say this is like a, for example, feeder, right? So you have to see like, if only with this one, this many houses, then you need a point here with a feeder. That's you need to have a switch here. And you say like, with this switch, I mean, you can say it could be either isolated or it could be connected to the main grid. If you would like to have like a feeder level, you need a switch at some point. So that's, you just need to find a point where you could either connect or disconnect with the main grid. And then that area could be a microgrid. And as I say, like even it is a single house also could be a microgrid. But it just depends on your requirement, and also that the area or the community that you'd like to design it. And also you should have a point that you can disconnect from the main grid. So that's the point. I mean, you need to find it out. Otherwise, you just can't cut somewhere from the main grid. So you need to find a suitable point to do that. So again, these are the sources I already mentioned, and you can see like most of them are clean source. But again, I mean, we have got a small diesel and gas as well sometimes. You could also use like a micro turbine, fuel cell, PV, wind, hydro, biomass, and storage mainly popular in current days, either battery or thermal, but hydrogen could be utilized as a storage. There are some other as well, like a mechanical storage as well, but I think that still is not that popular for microgrid. In microgrid, as I said, like energy storage, that's a a important component of a microgrid. Now, depending on the size of the battery, it could be utilized for different application, and also depends on like the operation that you need. Is it you need in the range of second, in the range of minute, or you need like for hours, or even could be days or month? Do you need in the range of like
Hello, am I audible? Yeah. Sir is having some issue. He'll join in 2 minutes. Just wait for him. By that time, let me just. Tomorrow we'll be having Valerie 3 to 3:30. I'll share the link with you all by today evening, along with the schedule. So kindly make it convenient to be there. I would also be looking for some participants to share their view about the program. And today I'll also be sharing the feedback form. So kindly submit it at the earliest.
Am I audible here? One is coming.
Yes, yes. Audible.
Yeah, he'll be joining in a minute. We'll just wait for him.
Right, sir.
Welcome back, sir.
I'm so sorry. I mean, it's just giving me that information that WebEx is having a problem, and then I don't know. I mean, my computer is automatically shut down. But let's start again. And sorry for that inconvenience.
So your computer hanged directly?
Yeah, I mean, it didn't happen previously. I just couldn't understand why it's like automatically shut down. Sorry, I mean, Altaf, so you can hear me now, right?
Yes. Visible and audible.
Again, I mean, I was talking about like the application of different ratings of energy storage system for mainly for microgrid. And the things that I would like to say that if you want like storage in the range of like 1 to 10 megawatt, probably that technology you might choose like that, here like flow batteries, or even could be like lithium ion. I mean, use lead acid, but that lead acid has got some issues. So if you want for longer period, then I think flow battery is better than lithium ion. You could also think about the flywheel, which is like a mechanical, but you could also use like a longer duration. If you want like very fast energy storage, then that super capacitor, that might be a good option. But even if you want like higher capacity, then in a pump hydro or compressed air energy storage, that is also getting popular in recent years. So you could think about those storage as well. And then thermal storage like a heat pump, that is also getting popular in recent years. So when you are thinking about like microgrid, some of the things you need to think if you would like to have microgrid, and these are some of the performance characteristics. So the safety, security, reliability, sustainability, cost effectiveness, and resilience. So resilience and reliability, these are like quite similar terms, but it has got some difference. So reliability means like when you have system have got like small scale disturbance, and then resiliency when you have got like low probability but high impact devices. For example, like it could be a tornado, it could be a for example other big event like a bushfire or flood. So when have this type of event, and its impact is measured in terms of resiliency. But some like small like one of the transmission line is off, or some disturbance in the transmission line, and in that case that continuity of power is actually measured by this index, which is called reliability. And I believe, other things, are well known to all of you. It has got some environmental aspect because it uses land as well. But again, some country which has got limitation, that might be one issue. Yeah, mode, that's I already mentioned, that's either grid connected or off grid. And here you could have a switch, or there are some other even modern device that I'll be talking later. Also, you can use as a microgrid connector with the main grid. So in grid connected mode, all these switches are closed, and feeder, are supplied by either from local source or from the main grid. And this is Icelandic, that here main switch might be off. Then you have only option to supply from the local sources. And sometime if you don't have it, some of the part, might be disconnected, just to make sure that it balance with the demand. Yeah, in terms of AC and DC, it could be two types, either AC microgrid or DC microgrid. But as like the traditional microgrid is AC, most of the existing microgrids are AC type. But as I say, DC microgrid also getting popular. Another reason that most of our load is also AC, although we have got some DC loaded as well. So if you have a AC microgrid, you will have a AC bus where your AC load might be connected directly, or might be having a transformer and step down and then connected. Or if you have a DC load, you need a AC to DC converter. If you have a energy storage, also you need AC to DC, DC to AC converter, because this is AC. If you have a DC generation, for example, photovoltaic system, also you need DC to AC converter. And all of this, need control, to regulate the power flow, and also control the voltage, frequency, power quality as well. Other option, as I said, again, it could be a DC microgrid, and it has got some advantages as well as challenges as well. DC microgrid would have lower losses compared to the AC microgrid, because that for DC there is no inductor capacitor, so the impedance would be lower, and you'll have got less voltage drop as well. And as I say, some of our generation is DC, so you can connect directly through a DC to DC converter with less conversion, and that will help to improve your efficiency. But if you have a AC, then definitely you need AC to DC, like a rectifier to convert to DC. Energy storage also you can connect directly through a DC to DC converter. And if you have a DC load, you can connect directly. Otherwise, if it's AC, then you need a inverter. So these are the performance parameter you can think about when you are selecting that whether you should have DC microgrid or AC microgrid. And these are the some performance parameter that can help you to choose which option might be better. So in terms of conversion efficiency, cost, transmission efficiency, power supply reliability, controllability, load availability, and protection. And these are the comparison between AC and DC. So if you think about the conversion efficiency, as I mentioned, that DC have got high conversion efficiency because you need less number of conversion. AC is conversion efficiency lower than DC because you need multiple AC-DC conversion. All the power electronics inverter converter are very highly efficient, but still there are some losses. Cost on inverter, for AC it would be higher because you need not only DC to DC, but also inverter as well. For DC, the cost would be comparatively lower for converter. Efficiency, transmission efficiency, as I said, for DC would be higher because it does not have any reactive power. But for AC, it would be lower because it has got loss due to reactive power, reactive current as well. Reliability for AC, for DC, I mean, it have got, you know, very smooth transition with DC power supply. With, I mean, when you are thinking about, you know, connecting with the main grid and disconnected. Controllability in DC is easy to control because there is no frequency, there are no reactive power, there are no phase unbalance issue. For AC is comparatively difficult to control because it has got voltage control, frequency control, unbalance issue, load availability. Most of the load we have got are AC. Number of DC load is still comparatively low if you compare with AC. Protection for AC, we have got measured protection system because our original system is AC. But for DC, I mean, it's relatively deep complex, and there are a number of research on going on to develop reliable protection for DC microgrid. And this one other option could be that you might have both AC and DC, which is we call hybrid microgrid, or sometimes we call AC-DC microgrid, where you have got both AC buses as well as DC buses. So DC buses is again like same as like a DC microgrid. So most of the DC sources you can directly connect with the DC bus. You can connect all the AC bus and AC load with the AC bus, and that will give you even lower conversion from DC to DC. And then you need a interlinking converter, which is bidirectional, which will connect AC and DC. And by controlling, you can regulate power flow either from DC bus to AC bus or vice versa. And this is the point of common coupling, which could be connected with the main grid. So even like in terms of the reliability, I mean, even that one would be might be popular than having either individual AC or DC. Is there any question or comments so far what we have discussed? Okay, if not, then let's continue. So the next thing I'd like to talk about that microgrid control. And as I mentioned, like this is very challenging to have very reliable control for microgrid. So if you think about the whole microgrid control, we can classify into 3 different types. It's called primary, secondary, and tertiary control. Sometimes also called level 1, level 2, level 3. But even like in primary control, it also can have some inner loop control, which is called level 0. But mainly level 1, level 2, level 3 are widely, I mean, known to all the people who is working in the microgrid domain. And here it shows like there's some overlap with all of this. So it's not like completely separated control. Now again, I mean, before talking about control, let's see, I mean, what are the operational priority for a microgrid. So the first priority that microgrid would like to have, and even that is being achieved from this control, that's why I'm mentioning here. that the first priority is that reliability. This is the first priority. I mean, when you are thinking about your designing and operating a microgrid. And reliability, that's again, I mean, related with your stability and equipment safety, which ensure that all that facility you have in microgrid, such as power electricity inverter, converter, transmission line, energy storage system, that are not damaged, even there is a disturbance there. Okay, so you need to make sure that your system are safe for all the equipment as well as the operator, and also it ensures stable operation during normal as well as some abnormal condition. So that's the priority you need to fulfill now. I mean fulfill first, and that has to be achieved through your reliable control. So the second function, once you have your reliable and stable system, so the next thing you can think about to make the system like having even better control is like a plug and play. And also you can think about having maximum renewable generation from all the devices connected with the microgrid, and how we can do that. We already talked about maximum power point tracking control and so on. You could also think about maintaining the state of charge for your energy storage for having longer lifetime. But the first, your priority would be making the system stable, even if you can't, have your desired state of charge. So that's not your first priority. That is like your second priority. So the first priority, whatever you can get it from those devices, make sure that your system is stable and safe. And the third priority, then once you have got your safe and stable microgrid, and also you're having your maximum generation like MTP, working well, you are maintaining the battery, SOC maximum minimum limit, you're having your plug and play control. Then the third thing you can think about, even like let's make the system like optimized. So once you have got optimized system, even it would be more cost effective. So that would be your third priority, and that also help you even like to better control and better maintaining the voltage and frequency range. Now the first control that I mentioned, this is like a primary control, or we call it local control as well. That's a level 1 control, and the main objective of level 1 control just to having smooth sharing of power among all the DC unit. So as I mentioned, like in most of the cases, you have got more than one sources. So, and most of them are connected in parallel. So you have to make sure that you have got like your desired power is sharing option. So whatever power you can get it from different sources, they are actually sharing the power among themselves. And other function of this primary control to maintain the voltage within the range and also the system frequency. How we can design primary control? Again, you have got mainly, if you classify, there are two methods. One is called Drupe-based method, and another is non-Drupe-based method. So the Drupe-based method is more like decentralized. So when you are designing the control, for example, let's say photovoltaic system, you don't know what is happening, like other photovoltaic system or wind turbine or battery. So you are not using any sensor communication to bring signal from other devices and then control and again sending back signal to other devices. So it's just doing everything locally. So that is mainly done through this, Drupe-based method. Non-Drupe-based method, you need some some level of information from other devices. And this is some of the method that's already been presented in the literature. Here, I mean, I'm just given some example. For example, like you can have like conventional group control. You can have adjustable load sharing control. You can have voltage power group, frequency, I mean real power, frequency, reactive power band group, virtual frame. There are so many methods. That's like adaptive voltage control method. This is again some of the example, but you have got more than that in the literature. And in the non-group, you have got centralized master-slave control, averaging load sharing control, circular chain control. But here also I'm just giving some example. You have got some other technique in the literature as well. But all of them, I mean, they are objective, mainly these two. So your, I mean, group-based method and those things are quite simple. But here again, I'm not talking about all of them. I'll just talk like few of them. I mean, how you can design this control. So for example, let's think about that. You would like to have a centralized control. So you have a microgrid where you have got all the devices, but you want to have a control in a particular centralized location. So if you would like to do that, so what you need, I mean, you need some sensor. That's probably you always need to measure some signal sensor. I mean, to measure voltage, current, whatever you want to measure, devices. And then what you are doing, I mean, you are measuring signal for all the devices, bringing back to the centralized control. So here, let's say this is like the device 1. You might have n number of devices. So you are bringing back all the signal from all the devices to your centralized controller. And then what you are doing here, that you are designing the control and processing all the calculation here. And then once you process, again, you are sending back that control signal mainly to your converter, which will control here voltage, frequency, as well as power sharing among all the devices. Now, as I said, like why? I mean, it is challenging because as I said, like in the microgrid, in most of the cases, the devices we have, it has got very low inertia or sometimes even like a zero inertia. And when you have got very low inertia, if something happens, I mean the system, I mean all the parameters deviation becomes quite high, and the system reacts very fast. So that's why even for microgrid, the controller that we have, we need also very fast acting controller, because if something happens, it can take the operation immediately. And when you have got like a centralized control, definitely, I mean, you need higher bandwidth and also very reliable communication, because if something communication lost, I mean, you won't be able to get any signal, and also the control that you'll be designing, that will also miss some information, and that might not be giving like in a robust performance. So having reliable communication, that's a, I mean, highly demanded if you would like to have centralized control. So the other option for non-group is like called a master-slave control. So the master-slave control means that one of the devices, I mean, they will act like a master, and all other devices, they will follow that, the master controller. So here, so the way that it works, so for example, let's say here you have got like, this is like all the devices that you have, So for example, let's say this is your master controller. So what this master controller does, it actually control the voltages for that particular system. And then at the same time, what it is doing, it is also making reference for all other devices. And then all the devices, it just follow the command given by the master. So this is the main idea while you're having like a master slave control. And also, like, what can happen, like if one of this, like, I mean, if slave fails, I mean, it will not have severe impact. But if master fails, the way that it designed, so the next one, I mean, it will take the role of a master, and then the remaining one will just follow that, master control. So that's why, I mean, this master slave control works. You could also have like a circular chain control. So the main difference with the previous one, all the, I mean, reference for remaining of the devices except the master one was coming from the master. But here the way that it does, for example, the second devices, it will get the reference from the first. The third one, it will get reference from the second one. So that's why it was like a chain. And the last one, again, you're getting reference come from the first one. So that's why it will be like a circular chain. That's why this control method, it is, I mean, known as circular chain control. So again, this is more only the primary control. But so far, is there any question or comments on microgrid control or primary control?
Sir.
Yes.
Nothing, sir. It's fine.
Okay. Thank you. So the next control I mentioned, this is like a secondary control. So you have a primary on top of that. You could also have a secondary control. Now, in terms of the research, I think so far many research have been done in the primary control. So if you would like to work on the microgrid control, then I think better option now go for secondary or tertiary level control. Because primary level, I mean, already so many have been done, and many of them have already implemented commercially as well. And the main function for the secondary control is more like the microgrid energy management. So you can maintain manage the energy. You can also maintain all electrical level within the acceptable range, like voltage, power quality, everything. And also it does another function that I mentioned, another problem, that synchronization of the main grid, that is also being done with the secondary control. And again, here I have mentioned, some of the methods that's being proposed in the literature, but as I said, this is some of only example, but there are many other methods available in the literature as well. For example, here, genetic algorithm, particle swarm-based optimization, model predictive control, and colony optimization. There are many, I mean, multi-agent system that's my student talked about yesterday, because this is more like the energy management. That's why, I mean, you need some optimization here as well on top of with control. And we have got distributed cooperative control. This is also like another popular technique. You also find in the literature as well. Now the secondary control, as I mentioned again, I mean, this one also could be either centralized, or even it could be distributed. Now, as I said, like you have primary control with all of the devices, and then on top of that, you have got another control, and there, this one again, I mean, here saying like this is like a centralized version. Now here, what it does, so again, I mean, it gets information from, if you have a centralized, all from all the devices, from all the batteries and everything that is coming as a input here. For example, you can have like a forecasting for all non-dispatchable generation you have got in the system. You could have some forecasting of the electrical and thermal load, SOC level in the EV, or in your battery, the operational limit that you need, because as I said, like this is maintain the operational limit as well, and different security reliability constant. You could also have some information from the main grid interconnection status, whether it's connected or disconnected from the main grid, and the energy price forecasting as well. So all of them can be as an input, and then definitely we will have some microgrid model settings and all those things. Then here you will process your microgrid, and then if you would like to manage energy, you could send some commands to the load to having like demand size management, on, off, or shifting the load, and other things also you can do. You will be giving a reference for all the primary control that you have, I mean, in your system, and based on that command, I mean, sometime it can have different set point. For example, let's say when this microgrid says that finding that something new load is coming, then it will give instruction to all the generator to different set point to have like more generation or sometimes less generation, based on like overall whatever happening in the whole system. But as I said, like instead of having like centralized, because here, as I said, like you need very reliable communication with all the devices. That's why you need a very high bandwidth and accurate communication. That sometimes make the system more costly. And also, as I said, like if communication fails, you will not get your desired performance from the controller. So another option could be that instead of using like centralized, you could use like the distributed control, where I mean instead of having like centralized like that, having getting signal from all of these devices and processing and then reapplying, and the initial one that I mentioned, like only decentralized, like whatever happening, you are just measuring signal here and then providing control signal locally. So instead of doing that, because both of them has got advantages and disadvantages. For example, here you don't need reliable communication, but at the same time you are not having any idea what is happening in other cases. So that's why sometimes it happenings other cases, and this control don't recognize what happened here. So that's why sometimes it cannot provide you a very reliable operation. This one, I mean, as I already mentioned, like it's having information for other subsystem, but at the same time you need very reliable communication, and if communication fails, it is becoming like a decentralized. But for this one, it actually combine the advantage for both these two. So what it does here, this one, instead of having information measuring from all of the devices, it does only share signal with the neighboring system. Like this one, it is just share signal with the neighboring 2 units. Same like this one, it will have sharing these two. So you need communication, but here you need limited communication. And that's how, I mean, this one is even getting more popular in coming years. So it needs like less bandwidth compared to the centralized one. And then the last control, which is like the tertiary control. This is more like while you are having like multiple microgrids. So it's not a single microgrid. You have got multiple microgrids which are interconnected. And if you want to coordinate their operation, then you need that tertiary control. And also sometime exporting, importing power with the main grid. And to do that, I mean, you need the tertiary control. So that's the main objective of the tertiary control. Either energy, sharing with the main grid, and or when you have got more than one microgrid, and then if you want to control power flow, then I mean you need that tertiary control. And here these are the some of the method. This is just some example, but there are many other methods you'll also get in the literature as well. So that's, I mean, in brief about like the microgrid control. But later also I'll show you some example. But as you know that designing control always needs model, and that's why I mean this is something a little bit complex to understand. But having said that, still I mean I'll show you some example. But before that, like, is there any question or comments? Any question or comments?
No, sir.
Okay, thank you. So the next topics that I'm going to discuss, that is also very challenging. That is islanding detection. And in this area also, I mean, people are having many research projects, because what happened, as I mentioned, that if you compare with the main grid, microgrid size is comparatively very, very low. Sometimes, as I said, like it could be few kilowatt, but as you know that the grid size like a gigawatt. So sometime, if it's just disconnected from the main grid, sometimes it's very difficult to understand whether this is like, this is grid connected or is operating in the isolated mode. But I know that when it is isolating mode, I mean, its control operation is significantly different from the main grid. So that's why it is important that, we identify detection accurately. Otherwise, it can damage the equipment, because the control also needs to be switched, because you need different control when it's connected grid and when it's off grid. Now, how we can detect island? Here, it's given, some of the methods that you can utilize. So initially, we classify into two types. One is called remote technique. Another is local technique. And local technique also three types. It's called passive, active, and hybrid technique. I'll just briefly discuss each of the technique. I mean, how it works. And again, I mean, as I said, like, why you need to do that? Because as I said, like, it could be a safety issue, and it could be also safety not only for line worker, but also for the DC sources, power electronics, inverter, converter. The voltage frequency may not be maintained with the standard permission level. So that's why it is important that, we identify that I mean, accurately. And again, I mean, other issues also like that. the synchronization issue, that might happen as well. And when it goes like, out of phase, sometime you could have like a very large mechanical torque and current, which might damage your generator, prime mover, everything. And sometimes it can also have, high transient as well, over voltage. That can have negative impact on your overall performance of the microgrid, as well as all on all the appliances as well. Now, the technique that I mentioned, that one of them is remote island detection technique. Now, as it mentioned remote, that means that if you like to do something from remote, you need communication, right? So this one actually based on your communication from your utility with your all the DGs. This method is quite, reliable, because you are using like continuous communication, but at the same time, they are expensive to implement, and that's why this is not uneconomical. So the way that you can do, you could have a basic idea of transfer trip scheme, where you are monitoring status of all the circuit breaker, which is actually using to connect the microgrid with the main grid, and recloser. That is, you are just monitoring whether this is on and off by sending signal from remote location, and that's how you can say whether it is grid connected or off grid. And to do that, that your SCADA system can be used to do that. So this one needs a better interaction between the utility and all the DGs, and that's why, as I say, it increases the cost for utility as well as for the DG owner. Another technique you can also use for your remote islanding, using power line signaling scheme. So that through power line, we can also transmit signal as well with a limited bandwidth. So here also, what you can do, that here you could have a transmitter, and then with all the DGs you could have a receiver. So if this switch is on, then you are continuously receiving signal here, but in some cases it is off, you are not getting any signal to your receiver. So that's how also you can say that this is isolated mode or this is grid connected mode. This to remote technique based on your transferring communication signal from a remote location. But as I say, this is quite expensive. Then other technique you can use, that is called local detection technique. So the local detection technique is mainly dependent on measuring some parameters locally. For example, voltage, frequency, power quality. And here, as I mentioned, there are three types of method. One is passive, active, and then hybrid, which is nothing but the combination of active as well as passive method. So the passive method, it works measuring some parameters, such for example like a variation in voltage, variation in frequency, variation in harmonic distortion. But what happened, when the system is microgrid is connected with the main grid, the variation that you will find, that would be very low variation. So you will have some threshold from your experience that when its system is connected, these are the maximum variation you can get due to the changing load or some internal small disturbance. But if it goes beyond that threshold, then your system might be in isolated condition. But the problem is sometimes when you have a slightly bigger microgrid and your load and source are almost equal, in some part of that system, you might not detect that like Icelandic correctly. So there might be some non-detectable zone where they might fail to detect the Icelandic condition. So here, these are some of the things you could utilize, as I say, rate of change of output power, like with respect to time at the DC site. And as I say, it would be greater than when it is connected with the main grid. Same for rate of frequency. It would be much higher when it is isolated. And also it could be the rate of change over rate of change of power as well. That also could be, very high. So using those changes, I mean, you could determine whether it is a grid connected, or because those changes actually depends on balance between your demand and generation. But if any mismatch happens, I mean, you will have get higher rate of change of either power, voltage, or frequency. But as I say, I mean, those have got some disadvantages. Some zone might be non-detectable. So other method you can try, like that active detection technique. So active detection technique, again, I mean, can be detected under even like the perfect match of generation and load. Although your microgrid have got same load, same generation, but still, I mean, using this method, you can accurately identify the Icelandic condition. And what it does that here, that you'll make some small perturbation in the system that will result in significant change in the system parameter when the DG is Icelandic. And that's how you will be identifying the Icelandic condition. And some of that could be that you could use your reactive power export error detection. That is like one of the schemes that you can use under that. So as you know, the DC generates a level of reactive power flow at the point of common coupling between the DC and the grid. But this power flow can only maintain when the grid is connected. So Icelandic can be detected that if you have if that level of power flow is not maintained at the set value. So that is one of the way that you can detect. Other one could be that you are, as I said, like, you could also make some perturbation in the reference signal when it is disconnected, and any changes in the reference signal also make a bigger changes all the output signals. So that's how probably you could also identify Icelandic condition as well. But the other one could be that using the hybrid method, the initial one, as I mentioned, like the passive one, you could utilize just to say like whether it might or might not be Icelandic. That will give you. So once you say that there might be a Icelandic, then you can even make sure by applying the active technique. So initially you are applying passive, then you are applying active technique just to make sure that it is actually really Icelandic condition, which is called actually a hybrid scheme. And as I said, this is just like the combination of these two. And here, this is again just summarize like relative advantages and disadvantages of all the techniques that I mentioned. For example, like a remote technique, local technique, and under local technique, passive, active, as well as hybrid. So in terms of like, reliable, as I say, like, this is highly reliable. Disadvantages, this is expensive, as I mentioned, and this is some example technique that you can utilize. Passive one has a very short detection time. Also, you might have some non-detectable zone. That non-detectable, that's the disadvantages. But advantages, as like, you can detect with shortly. You don't have to make any disturbance in the system, but it is accurate when there is a large mismatch in the generation and demand. And here, some of the things that you can utilize, as I say, like rate of change of output power, rate of change of frequency, frequency over voltage. You can use any of them, but these are the disadvantages. And one of them I already mentioned, some non-directive zone. And also something special care has to be taken while you're setting the threshold, because you are saying that when this is something more than that threshold value, I mean, it is having isolating condition. So you need to have good experience about setting that threshold. And then active technique. This is like, you in most of the cases, you'll not having any non-detectable zone, or even if you have, it will have a small non-detectable zone. And here some of the method I mentioned, and one of them is reactive power, but there are some other method as well. And these as I said, you have to make some perturbation in the system. So that's why you're making some small disturbance in the system. So that's how it will, for a shorter period of time, it will having some impact on the operation of all the devices. And the last one, that's the hybrid technique. Even if this one would be, more accurate than all of this method. I mean, not that one, but that passive and active technique. So that's all, I mean, for Icelandic detection. Is there any question or comments? So if not, but before,
Sir,
yes, yeah.
sir, can you just name some artificial intelligence applications on this remote islanding? I mean, the islanding techniques.
Remote islanding technique. I mean, the remote island technique.
Islanding detection, something.
So if you'd like to use like, artificial intelligence. So that if you would like to use artificial intelligence, I mean, what do you need? You need your like historical data, right?
Yeah.
That historical data that you need, for example, like when it was grid connected, what sort of like the data it has got for it. It could be, as I said, like either voltage, frequency, or power. And then also you need some data for Icelandic condition as well, and that's how probably you can train your system, and then that's how probably you could utilize those historical data. Based on that, you can analyze and you can identify Icelandic condition. But the one that I was talking about, the remote, that is more like a online type of detection. It's not like offline. So you are just continuously monitoring the system using your IoT devices communication, and through that you are just saying that it's like you're sending signal like a 1 or 0. That's how you're saying that this is either offline or online. But definitely, you're right that you could utilize those artificial intelligence technique, for the detection of Icelandic as well.
Okay, sir.
But here, the things that I mentioned, that is just like a concept, but the
Yeah.
technique that you can apply, again, it could be so many different techniques that you could, apply just to, implement that concept.
Yes. True, sir. Okay.
Now, just before showing that, microgrid research, many time I just talk about power system modeling and also like, you know, a linear system, non-linear system. So any type of power system model, actually we could represent that using this, like, you know, differential algebraic equation. So this is the differential equation and this is the algebraic equation. Now here x is nothing but that state variable, z is the vector of algebraic variable, and p is the vector of system parameter. So any system you have got, actually you can model like this. Now why you need that? Because to do further analysis, like, you know, designing control, I mean doing stability analysis, you need that mathematical model. So here this is actually include everything like modeling of all system component, generator, transmission line, transformer, loads, all the control devices you have. Finally you can have some differential equation, some algebraic equation. And if you would like to analyze stability, I mean, we can consider that, you know, this is that like a system model, where this is, as I said, this is the state vector, which is function of state, as well as this is time varying component. Now, for any system, I mean, you could have this like a 3 scenarios. Like the system operates like a before the disturbance, like you, for example, let's say, I mean, you are having a power system, but you are not having any issue. Everything is fine. For that, you have a like a equilibrium point. What's equilibrium point means that it has got a very steady state, voltage value, power value, frequency value, all are like in a very steady state. Next, when we do stability analysis, what we do, that we make some disturbance in the your original system, and after that disturbance, definitely there will be some system dynamics and transient. Now what happened, like, you know, if that disturbance are, you know, removed, and after the disturbance the system goes again like in either previous equilibrium point or a new equilibrium point, then we call that this system is stable. And if it doesn't, then we say this system is not unstable, and that we can do it many different way. And one of the way that we can do it, that is actually we call it small signal stability. And under small signal stability, one of the technique we widely use, that is called eigenvalue analysis. I'm not sure you have heard eigenvalue analysis, but if you would like to do eigenvalue analysis, or if you want to design any of that linear control, so the first thing you have to do, you have to make the system linearized. Because as I said, that's when you have got multi-machine power system, and that is true. We don't have any single machine system. In most of the cases, our system have got multiple machine, multiple transmission line, multiple load. And when you are model all of them together, that system becomes highly nonlinear. And analyzing nonlinear system is quite challenging. Even if you would like to analyze stability for the nonlinear system without making linearization, it is quite very complex. So that's why, I mean, we converted it to a linear system. And if you would like to linear the system, so the first thing you need to know all the parameters for a steady state condition, which is like not having any changes in the system, like when a system having everything is fine. So that's like the initial operating point. and that all the initial values. And then we are representing that equation, something like this, where you have got your dynamic equation, like a differential equation, and then where you have having some algebraic equation as well. Now, to linearize the system, we have got more than one method, but one of the techniques that we use from that, using the Taylor series. Again, I'm not sure you have heard about that. But what happened? If nothing is changes in the system, then if you differentiate any constant value, what we will get? We get 0, right? So when the system not having any changes, that means in equilibrium point, if you differentiate, that will give you a 0. But if you make it like a small changes, like where your system like having a very all like a constant value, that what we are doing, we are just making a small perturbation. Now once you have a small perturbation, like the equation that I have shown, we're just adding that small perturbation with your state as well as input, and then this equation using Taylor series we can actually represent by this equation. And then again, as I say, like this is 0 because this is steady state, and then just doing some simple mathematical, actually you're getting like this sort of equation where you have got some matrix with that, and how you are getting this matrix is given by this equation. So at the end, what we need, we just need those matrices, and once we have those matrices, we can have that transfer function by just using Laplace transformation, and then at the end that will give you, this is the transfer function. And once you have transfer function, if you find like this is the like a equation, like even and then that's the characteristic matrix. And once you have that, and if you just calculate the eigenvalue, that will give you whether the system is stable or unstable. Any question or comments on the step? Up to that stability analysis. And probably I'll stop here because we have discussed already so many things. So the remaining part, I'll finish tomorrow. But if you have got any question or comment, so far, what we have discussed, feel free to, share with us.
Sir, are we actually linearizing the system using Taylor's expansion, maybe in a practical scenario?
Taylor series, that's like, this is one of the very old and established technique, but there are some other methods, for example, like, some perturbation technique, that is also, another technique we use. But I think if you'd like to work, in the stability or control side, I think this would be like very basic method that you can start with. And also MATLAB, they have got many function. For example, if you just say like EIG eigen, it will automatically give you that eigen value, and through that you can easily say like the system is stable or not.
Yeah.
So,
Sir,
yeah.
when we linearize a system around an operating point by Taylor series, won't that be very much dependent on the operating point? But we won't be. There's
Well,
a
as I
very
said, like,
minimal.
because there is no other way. I know that this is not like sometime this is heavily dependent on the initial operating point. So and what we are doing, that we are just making little bit shifting on the operating point. So when I say like plus delta x or plus delta y, we're just making a small perturbation, and then just making it a small perturbation, then we are saying like with that perturbation whether it is stable or not. And as you select, this is heavily dependent operating point. So the operating point that we are choosing, so if that is very close to unstable region, then with that small perturbation that might give you the system instability. But if it is not, then so this is not like very smart way to do it, but we don't have any other, simple option to do it. So even if you do this one, at least it will give you some idea, like whether your system is stable or not, and even if it is unstable, what parameter or what devices actually making a system unstable. Because let's say you have got a system where you have got thousands of devices, right?
Yeah.
So how you can identify, like which one are actually contributing more to make your system unstable? So there are some, like through that analysis as I mentioned, I'll talk about that one tomorrow. But that method will give you some idea that you have got 100 generator, but which generator is contributing heavily to make your system performance bad or unstable. And then you can design the control for that particular system, or you can take appropriate action for particular system, so that you can have like an overall system is stable. Because as you know, the whole system are interconnected. So if something happen in one devices, the consequence or impact is not only limited with the particular devices. It actually goes to other devices, and that's how making the whole system unstable. And even if you're having blackout, what happens? Sometimes if you have a countrywide blackout, and that blackout already only initiate in one particular location,
Yeah.
right? And then your frequency, voltage, all goes outside the accepted region, and then it actually propagates to other part of the system. Sometime your protection system does not action appropriately, and that's how sometime state, sometime a whole country goes um, um, having like a blackout, and you're having without power, sometime even day, or even sometime it goes like a week as well sometimes. So this sort of analysis actually helps significantly. While you are doing stability analysis and developing control for a system where you have got multiple devices.
Okay, sir. Thanks.
So again, if you don't have any other question, I'll leave it here.
Jahangir,
Yeah. Yes.
hello. There are studies on
Sorry, Aldev, we can't hear you.
hello. Am I audible?
Now we are audible, yes, but we
Okay. Are there any real-time microgrids working?
there are so many. In Australia also, we have, even in our campus, we have got one microgrid. In my previous campus, also there is a operating microgrid. And in Australia, as I say, like there are like at least more than 20 microgrids are already operating.
Okay. Okay, fine. So we have a good future into it.
Definitely. That has got a very future. And recently, Australian government, they are actually spending heavily for mainly the remote microgrid. Because in Australia there are many cases like they are supplying 30, 40 houses using like 100-kilometer long transmission line, and those transmission line is already like 80, 90 years old, and maybe after some years they have to replace it. So instead of replacing this long transmission line, they are found that just building like locally small grid is much more cost effective. It's much more reliable. So that's why, I mean, even myself, I mean, I got a big project on a, I mean, initially doing, feasibility study, but also like partially real implementation as well. So we already have, got the project running, but it's only running for, couple of months. So for that particular microgrid, still, I mean, I don't have any real result, but the university microgrid we have got, I mean, I did have got some real result for that particular microgrid as well. And I was involved, I mean, when it was, implemented.
Can you also discuss how it was implemented? Because there are many faculties here. If somebody is interested to implement a microgrid in their own university.
Yeah, because see, as you know that, I mean, university, they have also committed to go net zero, right? And to go net zero, I think one of the potential option to go for a, like, campus level microgrid.
Right. Thank you.
Okay, then I'll leave it here. And hopefully I'll see you tomorrow in the final lecture. Thank you. Thank you. Thanks for your attention.
Okay, sir.
Okay, thank you all.
Yes, sir. Thank you, sir.
Okay, bye.
Please check your mail.
Proceed, sir.